We're going to continue with our continuity properties of functions, and we're going to focus in this video just on root functions. So we're going to be looking at number 3 here. It says for the nth root of f of x. That's how we would read that. We need to pay attention to this number right here. This is called the index of our root. We're really interested in if that number is even or if that number is odd, because that's going to tell us kind of how we need to proceed with the problem. So if n is odd, so if we look at the index of our root and we determine that it's odd, then the whole function, the nth root of f of x, is continuous everywhere that f of x is continuous. So what this means is I just need to look at this f of x. The whole function is continuous as long as the inside function f of x is continuous. So we're really just going to be interested in looking at just that part. That inside part. Is the part that's inside of my radical continuous or not? And we can use these two properties that we talked about up here with polynomial and rational functions to help us determine if the, quote, inside part is continuous or not. So that's the first of the two cases. The second case, if we look at the index of our root and we determine that it is even, then in that case our function, the nth root of f of x, is continuous everywhere that f of x is continuous. So let me just pause right there. Here we're saying the exact same thing we said above. We said we're looking at the inside part of our radical, and we want to say, where is that function continuous? So we're saying, where is the inside part of our function continuous? But now we have this extra piece. We need it to also be non-negative. And really that just means it can be 0 or it can be positive. It cannot be negative. And hopefully this makes sense. If we say something like y equals the square root of x, right? Here, if we don't write a number, we assume that the index of our root is 2, not 4. So the square root of x, and when we say non-negative, we're really saying, hey, we're not allowed to take the square root of a negative number, because if we do, we end up with imaginary numbers, and we don't want to do calculus with imaginary numbers. You can, but boy, it's going to make this class a whole heck of a lot harder. So we're just going to stick to real numbers. So really, we want the inside part to be continuous. We want it to be non-negative. Let's look at a few examples here. So first up, I've got g of x equals the square root of x minus 4. So just like I said earlier, if we don't have a number written right here, if we don't have that index, we say a square root, right? To square something makes me think of an exponent of a 2. So we have an even root right here. So an even root, we need to pay attention to two things. We need the inside part of this function to be continuous and non-negative. So the inside part of my function in this case is x minus 4. And I'm just going to write this out over here. The inside part is x minus 4. First, I want to determine what type of function this is. Well, this is a polynomial. So we said polynomial functions, it's continuous everywhere. So that's good. That means we don't really need to worry about that piece. So we know it's continuous everywhere, but the thing we do need to worry about, that extra thing, is we need x minus 4 to be non-negative. So when we say non-negative, what we really mean is that number could be 0, so x minus 4, it could equal 0. Sure, that's fine. Or it could be positive. Well, positive numbers are greater than 0. So what I'm really saying is x minus 4 can be greater than or equal to 0. So what I'm doing is I'm taking this inside part of my function, just the inside part. It doesn't really matter what's happening outside of this function right now. I'm taking the inside part of that radical, and I'm saying that inside part has to be greater than or equal to 0. And then I'm just going to solve this inequality. So here in this case, I can just add 4 to each side. I'm saying x should be greater than or equal to 4. So this is what needs to be true in order for this particular function to be continuous. X has to be greater than or equal to 4. So here, again, I want to encourage you to write your answers using interval notation. It's how I'm going to ask you to write your answers. If we were to sketch this out on a number line, we'd say, okay, here's 4. We want all of the numbers that are greater than 4, so that means we want all the numbers that are to the right of 4. And we do want to include 4. We see this greater than or equal to, so that means it is continuous at x equals 4. So if I wanted to write an interval for this highlighted section of my number line, I would say it's continuous on 4 to positive infinity, parentheses around infinity because we always use parentheses for infinity, and then we're going to use a bracket around 4 because it is continuous at 4. We said over here that it could be greater than or equal to 4. So it's continuous on this particular interval, on 4 to positive infinity. So that's kind of how we're going to think about these even roots. These are a little bit more challenging. I think these are the trickier of the two because we have that extra non-negative requirement in order to be continuous. In the next example, if I look at h of x, and if I compare it to the one above, it's actually the same exact inside function. All I've done is change the index of my root. Now I have the cubed root of x minus 4. So rather than the square root, I have the cubed root. So now, in this case, the index is odd. So all I need to worry about is this inside part. Where is this continuous? Well, we set up above that x minus 4 was a polynomial, and it was continuous everywhere. That part is still true, and you can write that down if you want to. X minus 4, that's still a polynomial, which means it's still continuous everywhere. So since it's continuous everywhere, okay, we're just going to say it's continuous from negative infinity to positive infinity. There's really no other work that needs to be shown here. Because I've identified that that inside part is a polynomial, I can just say, okay, it's continuous on negative infinity to positive infinity. In the case that we don't have a polynomial on the inside of an odd root, so if I look at this last part here, v of x, it says we have the cubed root of x minus 4 over x plus 2. In this case, that inside function, this is a rational function. And if we need to, we can scroll back and look at our notes. We can look at those continuity properties that we talked about earlier. We said, let me highlight it in a different color here. How about I highlight it in blue here? Rational functions are continuous everywhere except for x values that make the denominator equal to 0. So I'm going to look at that rational function that I came up with, which was x minus 4 over x plus 2. I know that that function is continuous everywhere except for places that make our denominator, x plus 2, equal to 0. So I'll take x plus 2, set it equal to 0, and solve this equation. In this case, I end up with x equals negative 2. It's a very similar process if I were just looking at that inside part, not even the cubed root. If I were just looking at this rational function, I'd be doing the same exact thing. So it's continuous everywhere except for x equals negative 2. If we need to, again, we can draw out a number line, and we can say, here's negative 2. It's continuous everywhere except for that value. So it's continuous on the left-hand side. So that left-hand interval, that would look like negative infinity to negative 2. Again, we don't want to include 2. And then for the right-hand interval, we would say, okay, well, on that right-hand side of negative 2, it's continuous from negative 2 to positive infinity. We'll put a u in between them to connect our two intervals, and there is our intervals of continuity. It's continuous on negative infinity to negative 2, union negative 2 to positive infinity.